Bethany Glesner, and I'm going to be a junior in the Material Science and Engineering department. I participated in the SURE program with Professor Richard Lane as my sponsor. I would definitely recommend the SURE program for students in the future because I learned a great deal and it was really good experience to feel what it was like to work in the lab full time. So on with my research. The goal of the current research being done by the Lane Group is to use nanopowders to create transparent ceramics that can be used in optical applications, such as lasers. To do this, the ceramic body must be 99.99% of the theoretical density. The work I did was with both alumina and yttrium aluminum garnet, or YAG, and this slide shows some basic information about them. YAG is a ceramic commonly used in lasers, optics, and high-temperature applications. Alumina is commonly found in nature, even as gemstones in a single crystal form, which have been used for many years in technical applications. Transparent ceramic alumina could replace single crystals and open up many more opportunities because more shapes can be made with ceramics than with single crystals. The alumina I have been working with comes in two phases, or crystal structures, the delta phase and the alpha phase. The delta phase is a high-temperature metastable phase, often used as a support material for catalysts. The alpha phase, also known as sapphire or corundum, is the stable phase at room temperature and is also used for many optical, structural, and electrical applications. All of these powders are made using a process called liquid feed flame spray pyrolysis, or LFFSP. Here's a diagram of this process, which begins with organometallic precursors that are aerosolized and burned, then quickly quenched to create nano-sized particles. The powders are suspended in a solvent along with binders and dispersed and then sieved to reduce particle agglomeration. Then they are uniaxially pressed into cylindrical pellets as shown. Each pellet is a small sample used for testing of the powders and processes. The pellets are then cold isostatic pressed to 200 megapascals and are then heated to 800 degrees Celsius to remove additives. Then they are sintered at much higher temperatures to allow for the ceramic to greatly increase in density, as well as allow for any necessary phase changes to occur. The density of the pellets before sintering is known as green density, and these have been less than the 60% which is required for successful sintering. I did a study over the summer to test different variables and determine their effects on the green densities. Variables I tested during the pressing of the powders are shown in this table. The results of the study are in terms of the mean green density that each variable had obtained, and the column on the far right shows how many of the 5 pellets made for each category remained after the final step. The 5 control pellets were made using about 100 megapascals of pressure for 1 minute with 2 weight % polyethylene glycol, or PEG, as a binder. 5 pellets each were uniaxially pressed at 50, 150, and 200 megapascals, and as the table shows, 50 megapascals was not enough to hold the pellets together. The categories labeled with times show how long I left the load on the pellets during uniaxial pressing. The Darwin C row shows the data for the pellets that I suspended with it. It is used to reduce the agglomeration of the powders and also keep the desired particles from settling out of solution. 5 of the pellets were made just as the controls, but were then kept in a desiccator after being pressed until measurements were made. In another 5 pellets, the amount of binder that was used was doubled to 4 weight % PEG. After taking density measurements of the pellets at various steps, I used a student's t-test to determine if these results were statistically significant, and the use of more pressure in the uniaxial pressing stage and the use of Darwin C showed a significant increase in densities. However, as you can see in the table, these green densities are less than the 60% required. The amount of uniaxial pressure used to create the pellets with the highest densities in my study was 200 megapascals, which is enough to cause end capping of the pellets. End capping is a result of the friction between the die wall and the powder and creates areas of high and low densities within the pellet as shown in this diagram. These will eventually split apart at their boundaries during further processing. Cold isostatic pressing is done after uniaxial pressing at higher pressures and will not result in end capping because the pressure is applied in all directions and without a surface to induce friction. Since our goal is to get the highest density possible, but we also need specimens that will survive the entire densification process, studies should be done to find what the most efficient uniaxial pressure is in terms of both density and quality of the pellets. Future work must also be done to optimize the process in the areas of sieving, dispersing, and sintering to get fully dense and transparent ceramics. To conclude, increasing the pressure applied to form pellets as well as the use of certain additives increase the green density, so this will be done in the future. More processing steps such as sieving will also be done to improve upon the green densities so that the ceramics can be sintered to 99.99% dense. Some of these steps have already been tested with YAG powders, and the green densities were improved by nearly 10% as shown in the table. With this improvement in processing and subsequent green densities, it should soon be possible to produce a transparent ceramic, and there will be even more possibilities for the applications of ceramics in technology.